Hey Islanders, welcome back to another episode of Islander Robotics, where today I'll be showing all of you how to create your very own binary tree. For those of you who don't know who I am, I'm William McKeon, and I'm an electrical engineering student whose passion for artificial intelligent robotics not only made me decide to switch majors to computer science, but also has put me on this journey to master Python. So sit back, relax with your favorite snack, and let's get started, shall we? So this week I decided to be a little bit of a mad scientist. Meaning this week's code's either going to be a complete mess or it's actually going to work a lot in our own favor. Reason being is because a lot of the data structures that we've been working with, like linked lists, queues, heaps, and even today's data structure, binary trees, all run off of a node class. So what I decided to do was make one node class that all these different data structures would rely on. And not only that, but binary trees have there's a lot of different types of binary trees, and a lot of them have a lot of the same similar methods that really can be combined into one parent class. One parent class meaning an object that holds all these similar methods that we will then be able to call upon from child classes to be able to access those methods. And by child class, I mean the various different binary trees. So let's see how this code worked out with starting. Alright, so here we are inside of the node module. Notice, just like all the other node modules that we've worked with in the past, like in the linked list, and including this one, it only has one method inside, the initializer for this class. And inside this initializer, we're going to be having 4 variables. The first variable that we're going to be talking about is going to be called the data, right here on line 5. Now, data is set to an input variable, also called data, and by default, we're going to set this equal to none, just like how we did when we created the node class for our linked list. Now, the next thing we're going to be talking about is also a characteristic of the of the linked list class, and that is going to be this next variable, which by default, just like the data, is going to be set equal to a variable inside of our input arguments, and that input argument is going to be called next as well, ironically, and we're going to set this equal to none. Now this is really where we start getting to the Frankenstein aspect of of this class, and that's going to be the self.left equals none and self.right equals none. These are not characteristics of linked lists or any of the closely related data structures of a linked list. Yes, a binary tree is I guess you could consider it a cousin of a linked list, but it's designed after a very different aspect. A linked list is very linear, where a binary tree is going to, like its namesake, is going to resemble a tree. And these left and right nodes right here are really going to allow the data structure to evolve into this really big tree or this really, really small tree. It really just depends on your data structure. And these left and the right are going to allow you to also have branch nodes and leaf nodes. So that being said, once we go into all the code, delete the old node classes and now import this new node class, we're going to now be able to actually get into the meat of today's video, which is going to be creating this class right here. And this is actually the parent class for all the binary tree data structures, and we're going to just name the class tree. All right, nothing too special. And then once we've named the class, we can get into the initializer of this class, and everything you see inside of this class, it's going to be pulled by all the various different children class that we're going to have for this one specific class. And so therefore, it's going to make a lot more sense, since they're all going to be initialized the same way. We want the initializer of all of them to actually be exactly the same. We're just going to create that one initializer inside of this class. And we're going to say def underscore init, just like how we would always do it. We're not going to have any input arguments for this init method. Instead, we're going to say self.root equals none. Reason being why it's called root is actually just like its namesake, a tree. A tree's roots are really the base of the tree. Therefore, the same idea here, where the very first node of our binary tree is going to be the root of the tree. All right, and really you can think about the self.root as, remember back when we were creating the linked list module, we had self.head equals self.head equals none, and self.tail equals none. Same things going on here, except we don't have a tail. Instead, you can really think of self.root equaling none as the same equivalency for a linked list saying self.head equals none. And once we've really defined this is when we can start getting into the other methods that a lot of the other the binary trees will be able to pull from. And that's going to start off with this method right here, which size method over here on line 8. For the size method, we're actually going to be having one input argument, which is going to be root. The reason being is because the size method, as well as a lot of the other, well, all the methods that we'll be talking about in today's video are going to be recursive. We're going to be a recursive call. And the reason being is because really in order to be able to traverse through any binary tree, we're going to have to be recursively going through it. And all of them are going to have a base case that's going to be very similar to what we have right here, where if root is none, meaning we have reached the end of that branch, there is no more data beyond that, we're going to return 0 in this circumstance of this method. Now, through the rest of the code, you're going to see all sorts of different return calls, but for this one for this one method, we're going to be returning 0. Now, underneath that, we're going to be having left size. Left size is going to be a recursive call where we're going to set this equal to self.size, and we're going to pass in the argument of root.left. All right. So the whole purpose of this recursive call is just to find out the size of the left side of the tree. Now, right size is going to be basically the same objective as left size, except we're checking for the right size of the binary tree. Then for the final return, we're going to say return left plus right size plus 1. The reason being we're doing plus 1 is because when we do that final recursive backtrack, we're going to essentially be subtracting 1 from the final sum. So in order to compensate for that minus 1, we're going to add that plus 1 at the very end. So now that we have the size method all ready and set, we can now start talking about the height method, which is over here on line 16. And it's very similar to the size method, except the objectives of these two methods are completely different. The size method, we are counting the number of nodes within the tree, and the height method, we're actually seeing how far the furthest node is from the root. And we're able to actually do this very similar to the same as what the size was, where we have a base case of if the root is none, we're going to return -1. And then we're going to have these two recursive calls where the left is going to be checking the furthest node from on the left side of the tree, and the right is going to be doing the same exact thing, except it's going to be looking at the right side of the tree. Once these two recursive calls are finished, we're there going to be able to actually compare the two, where we're going to say if left is greater than right, then we will return left plus 1. The plus 1 is the same compensation we're doing up above in the size. And then if right is actually bigger than left, we're actually going to return right plus 1. All right, so that's really what's going on. We're actually now going to be going into 3 really, really cool methods that's going to allow you to visualize what is currently going on within your tree. And they're called pre-order, post-order, and in-order. And they're all very similar, except their orientations are very different, all right? And really, it's not going to be the recursive call like what we're talking about over here on line 27. That's not what's going to be different. All 3 of them are going to have the same recursive base case. It's going to be the next 3 lines afterwards. So let's just talk about pre-order first. And the very first line that you're going to see on 29 is we're going to actually print the data within the current node or the current root. Once that data has been printed, we're going to therefore go all the way down the tree on the leftmost path and go until we hit none. Once we've hit none, we're going to recursively backtrack. And we're going to then go all the way down the right path of the tree. Once we've hit none again, we're going to then print out the data again. Now, the next 2 methods are actually going to be very similar to each other, except there's going to be a couple of changes. For instance, in order, we're going to go all the way down the leftmost path of the tree until we hit none. Then we're going to recursively backtrack to a node, to the previous node, and we're going to print that data. Once we printed that data, we're then going to go down the furthest rightmost path of that node that we're currently at until we hit none. Once we've hit none, we're going to repeat the process until we're completely done with the tree. Same kind of idea for post order. However, what we're going to be doing is going down the leftmost path. Once we've hit none, we're going to stop, recursively backtrack, go down the rightmost path, and then stop, and then print the data. All right, so really all you have to really remember is the orientation within pre-order, and then once you've memorized the orientation like print, root left, root right, all you have to remember is pre-order, in order, and then post-order, because the print statement goes down each time. There are two types of binary trees out there, a self-balancing and a non-self-balancing. And the two methods that we're about to go over are very vital for any self-balancing tree. For instance, we're going to start off with isFull. isFull is going to be a method that returns a Boolean value, meaning true or false. And really, we're going to be able to determine if the value is going to be true or false, judging by these three base cases we have right here. So if root is none, we're going to return false. If root.left and root.right are both none, therefore we're going to return true. Then we're going to continue on to the last if statement. We're going to say if root.left is none and root.right is none, then we're going to actually create a brand new recursive call where we're actually going to be using Boolean algebra to actually determine the final answer. This if statement is actually going to be the if statement that determines the final answer for this method. And the way that it's going to do is we're going to say return self.isFull, and we're going to pass in root.left for this one, and so meaning times self.isFull, and we're going to pass in the input argument of root.right. So therefore, the only way that this value is actually going to produce true is if both of these recursive calls both come back as true. If one of them is true and the other one's false, therefore we're going to get a false output. If both of them are false, we're going to get a false output as well. Alright, and then if by some chance all three of these if statements turns out to be false, then we're going to recursively backtrack with the value of false. The next method is just as important for self-balancing trees as isFull, and really that method is going to be called isComplete. And really isComplete is very similar to isFull. We're going to be returning a Boolean value. Again, that means true or false. Oop, I did something again. And that true or false value is going to be answered by one of these two base cases, where we're going to say if the root is none, we're going to return true, and then if the index is greater than or equal to the node count, we're going to return false. All right, and then the next two lines on line 60 and 61, those are going to be the recursive calls of our recursive function, where we start the next recursive call. And really, they're very similar to all the other recursive calls that we have made inside of this video. However, I really want you all to look at the input arguments of this method. More specifically, what we have for the input argument of index. And for left completed, we have 2 times index plus 1. And then right completed, we're going to have 2 times index plus 2. These equations or these algorithms allow us to be able to confidently tell where we currently are within our binary tree. So just like how you know what index you are currently in within a list or an array, this equation allows us to be able to have the same certainty. I can't speak. This algorithm allows us to have the same idea behind that. Then once those two recursive calls are completed and we're finally all the way back to the current once we're all the way back from those recursive calls, we're then going to return. Well, we're going to go on to the next line, which is going to be the final return. And just like isFull, we're going to be using Boolean algebra to determine the final value of this method. All the methods that we have talked about throughout this video are all the methods that are really doing all the hard work. Now what we're going to be going into is actually the methods that are going to be the driver methods for those methods. All right, and let's actually just talk about the size method, because a lot of them are very similar, where we're going to have one line. We're going to have methods that have literally one line, and in the circumstance of the size method, we're actually going to be returning self._size, and then we're going to also be putting an input argument of self.root. Now notice all the methods that we have talked about throughout this video have an underscore before all the names, and in this circumstance we're actually calling upon those methods. Well, one of those methods, size. The reason why we have that underscore in front of all the methods that we were just mentioning, well, the methods that we were just talking about earlier on in today's video, is because Python doesn't really have a way to signify that there is a private section of your code. So the way that us Python developers have been able to get around that is just by saying and putting an underscore before the name of a method, signifying to other Python developers that what you're messing with is a private section of the code. All right, and really you do not need these driver methods. The reason why I have them, and I suggest you have driver methods when you're dealing with a recursive function, I mean that's really why we have these driver methods, is because we're dealing with a lot of recursive methods. And the reason being is because if you don't have these driver methods, there's a good chance your code could end up getting very messy. More or less about as messy as my room used to be back in high school. Alright, and really that's all that's going to be going on for these methods. There is one driver method that's going to be pretty different compared to the other ones, and that one's going to be the driver method for is complete. And that really is because unlike the other methods that we've dealt with for today that have only had one input argument, is complete actually has three input arguments. A root input argument that's going to be getting a value of self.root, an index value that's going to be predetermined as 0, meaning the very beginning of our binary tree, and then the size method is going to represent the node count. Now, I kind of foreshadowed this earlier on in today's video when we were going over the size method, because the size method really is returning the values, really returning the node count we have within our binary tree. And really what we have now is the basis for any binary tree you could possibly think of. However, to actually create a functional binary tree, you have to know what type of binary tree you want to create. So join me next Sunday, where we will take this parent class to create not just one binary tree, but also two binary trees, a heap and a binary search tree. And essentially, you can think of these two as twins like me and my brother. So if you have any questions, go ahead and leave it down in the comment section. As always, thank you all so much for watching. You're all truly awesome, and we're very close to getting 200 subs. So honestly, thank you all so much for helping this channel grow so much. As always, happy coding, and I'll see you all in the next video. Bye.